This is section 4.2, exponential functions. We're going to begin by graphing exponential functions. So previously, we graphed quadratic functions, we graphed cubic functions, and now we're going to be graphing exponential functions. And you can see that our variable x is in the exponent. Okay? So, an exponential function is defined as f of x equals b to the x. So we have a base b that cannot be equal to 1 and has to be positive. And this function, b to the x, is called an exponential function of base b. Let's see how this works. We'll begin with f of x equals 3 to the x. So let's go ahead and just let x be 0, 1, 2, 3, and maybe -1, -2, -3. So here, f of x is 3 to the 0, which is 1, 3 to the first power, which is 3, 3 squared is 9, 3 cubed is 27. Now be careful here, 3 to the -1 is going to be 1/3. 3 to the -2 is 1/9, and 3 to the -3rd power is 1/27. So if we plot these points over here on this graph, as you can see, we have 0, 1, 1, 3, 2, 9, 3, 27, -1, 1/3. It's just very, very close to the x-axis. -2, 1/9, and -3. So now, as you can see, this graph looks like this. And this is y equals 3 to the x. Okay? And as you can see, this graph is steep in quadrant 1. And I always like to say that that's because the base is greater than 1. We'll talk more about that. Okay, let's look at f of x equals 2 to the -x. Keep in mind that this is equal to 1/2 to the x power. Okay, let's go ahead and let x be 0, 1, 2, 3, -1, -2, and -3. And so we have 2 to the -1, 2 to the -2, and 2 to the -3. Now notice this is 2 to the first power, since it's the opposite of that x, and 2 squared, and 2 cubed. So now, coming over to this graph, you can see that we have 0, 1, 1, 1/2, 2, 1/4, 3, 1/8, -1, 2, -2, 4, and -3, 8. And this is f of x equals 1/2 to the x power. Now, what do you notice? Here, I mentioned we were steep in quadrant 1, but here, the graph is steep in quadrant 2, and that's since the base is a fraction between 0 and 1. Okay, let's take a look at number 3. We have 1 minus 2 to the x plus 1. So we can go ahead and plot some points first, but then I want to talk about the transformations that have taken place. We'll use those same x values and maybe take a moment to fill these in. Okay, and we could go ahead and take a look first at this parent function. Y equals 2 to the x. So what we have, let's take a little closer look. We have f of x equals 2 to the x plus 1. Keep in mind, let's rearrange these terms. And this might look a little nicer. So what do you notice? Here, we will reflect across the x-axis. Here, we will go left 1 unit. And here, we will go up 1. Okay? So, as you can see, we will have 1 left, 1 up, and then we will reflect across the x-axis. Okay, so taking a look at this parent function, which is 2 to the x, and we can just put a few of those on the graph. 0, 1, 1, 2, 2, 4, 3, 8, and then of course we will have these smaller values. And this is f of x equals 2 to the x. So now we will take each of these points and move 1 to the left, 1 up, and then reflect across the x-axis. So graphing these points, as you can see, we have this beautiful transform graph, and here we have f of x equals 1 minus 2 to the x plus 1. Just a beautiful transformed graph. Okay, so now we're going to take a look at a graph that has a base e. So an exponential function with base e. And e is a universal constant, just like the number pi. Keep in mind that e is a number. It is not a variable. And it's called Euler's number. And it's approximately equal to 2.718281828. So now, if we would put this in our calculator, we could approximate these. So I'm going to make a note here. use your calculator to approximate. Let's see if we can bring up our calculator. And as you can see, we have E noted right above the divided sign. So we can have second E and then press the squared button. Whoops. Let's start over. E squared. And E squared is approximately 7.3891. Okay, how about E to the negative 3? And that's approximately 0.498. And then we have E raised to the root 7. And that's approximately 14.094. And E to the pi raised to the pi, and that's approximately 23.1407. So keep in mind, E is just a number between 2 and 3. Okay, so let's go ahead and fill this. Take a look at this next function, and we can fill in these table values. So we have f of x equals e to the x plus 1. So we have e to the first power. Well, that's just equal to e squared, and we just found that. E cubed, e to the fourth, now this is interesting. We have e to the 0 power, which is equal to 1, and then we have e to the negative 1, and that's 1 over e, and that's approximately 0.4. And then we have e to the negative 2 power. So we could actually put these on the graph here. And those will go up, and then we can try negative 1. And what do you notice about the steep part of this graph? The steep part of this graph is in quadrant 1. And why is that? Because the base is greater than 1. Steep in quadrant. And why is that? That's because our base is greater than 1. Okay? Here, B is equal to E. Okay, so now let's use exponential functions to compute compound interest. So we have our simple interest formula. We have compounding n times per year, And here we have what we call continuous compounding. So we will be using all three of these formulas. So let's take a look at number 9. We have $15,000 invested. So our principal amount is $15,000. We have 2.5% interest rate. So R is 0.25. We are compounding annually, so N is equal to 1, and we want to know how much is in the account after 7 years. So now we have the amount is 15,000 times 1 plus 0.25 divided by 1, all raised to the 1 times 7. And if you put this in your calculator, you will get $17,830.29. Okay. Now, let's look at compounded continuously. We still have our principal amount is $15,000. Our rate is 0.25 and our time is 7 years. So the amount is that principal amount multiplied by e to the RT. And if you put that in your calculator, you will come up with $17,868.69. So you can see that it is a bit more money. Okay, so now how about quarterly? What are you thinking? Well, we still have P is 15,000. Our rate is 0.25, and I think I made a mistake here. That should be 0.25, and that should be 0.25. I think my calculations are correct. That's better, and I had it correct over in the other problem. 0.25 and N is equal to 4 and T is equal to 7. So now you can see that N is equal to 4. So now the amount is 15,000 times 1 plus 0.025, and now this time that's divided by 4 multiplied by 4 times 7. Raised to the 4 times 7 power, which is 28. So here A is approximately $17,858.96. So it's not quite as much as compounded continuously, but it is more than compounded annually. And what can we write over here? and more than compounded quarterly. Okay? So now let's use exponential functions in applications. So plutonium, which is weapon grade, is composed of approximately 93% plutonium. The half-life of plutonium-239 is 24,000 years. In a sample originally containing 0.5 kilograms, the amount left after T years is given by this function. Evaluate the function for the given values of T and interpret the meaning in context. So A of 24,000 is equal to 0.5 times 1/2 to the 24,000 divided by 24,000 power. And so, if you work this out, this is 0.5 times 1/2 to the first power, and we'll come up with 1/4. What does this mean? This means after 24,000 years, which is 1/2 life, 1/4 of a kilogram, which is 1/2 of the original amount, remains. Okay, how about A of 72,000? Well, that's equal to 0.5 multiplied by 1/2 to the 72,000 divided by 24,000 power. And that's equal to 0.5 multiplied by 1/2 to the third power. And that's equal to 1/16. Okay, and so now the interpretation here is after 72,000 years, which is 3 half lives, 1/16 of a kilogram, which is 1/8 of the original amount, remains. And let's try one more problem. A 2010 estimate of the population of Mexico is 111 million people, with a projected growth rate of 0.994% per year. At this rate, the population, P of T in millions, can be approximated by this exponential function. Now keep in mind, T is the time in years since 2010. So if we are asked to evaluate P of 4, P of 4 is equal to 111 times 1.00994 to the fourth power. and that's approximately equal to 115. And interpreting that, we have that in the year 2014, so keep in mind, P of 4, when T is 4, this is year 2014. So in 2014, the population of Mexico will be approximately 115 million. Okay, let's try P of 75. That's equal to 111 multiplied by 1.00994 to the 75th power, and that's approximately 233. So in context, we have in year 2085, the population of Mexico will be approximately 233 million. And that concludes this section.